Why can we accurately predict the positions of celestial bodies centuries into the future, but fail to make accurate weather predictions for more than 1 week into the future? Is it because we just haven't figured out how temperature, atmospheric pressure, and wind are connected to another? Well, maybe in part. The real problem, however, is something else: chaos. Chaos was first discussed in the context of meteorology, but now chaos theory has applications in all sorts of disciplines. But what exactly is chaos? Say we have some point of data p with a subscript t to keep track of time. This data point might be a set of measurements like temperature, humidity, wind speed, and so on. Though to keep it simple, we'll say that it includes only 2 variables, called x and y. And we might have a good understanding of how these variables are connected to another, and can capture these relationships using a set of mathematical equations. That is, xt and yt are some functions of their past. This means that when we are in some period t, we can use these equations to work out where our data point p will be in period t plus 1. And given the point in t plus 1, we can figure out t plus 2, and so on. So in theory, given our initial point p and our set of equations, the future of p is perfectly predetermined. Right now, this might seem like the exact opposite of chaos, but bear with me. Now let's say that in addition to p, we have some other point p prime, which is almost exactly identical to p. Both points are governed by the exact same set of equations, and p prime differs from p only on the 10th decimal place. Surely, you may think these 2 points will evolve similarly over time. They will probably always stay near one another. But this is where chaos comes into play. For some sets of equations, the slightest differences in initial conditions can lead to vastly different trajectories over just a few periods of time. This entails that in a continuous world, or at least a world with many decimal places, any measurement which captures only a handful of these decimal places is just too inaccurate for us to properly pin down our initial conditions. This means that even if our mathematical models are perfectly fine, we are still going to get inaccurate predictions if we go too far into the future. Edward Lorenz, the founder of modern chaos theory, summarized this problem as: the present determines the future, but the approximate present does not approximately determine the future. Anyway, you probably clicked on this video because you would like to get started with a new coding project. So what is it that we are going to do? We are going to write ourselves some Python code that can find chaotic systems of equations, so-called strange attractors. And given these systems, we will then pass some data through them and then trace how the system evolves over time. The results are some rather stunning patterns, and it's these images that we are after in this project. There exist infinitely many of these patterns, and even though our computers can only generate a finite set of numbers, it's virtually impossible for someone else to generate the same patterns that you will create on your machine. So as you look at one of these pictures on your computer, take a moment to appreciate the fact that in all likelihood, you are the only human who has ever seen this image, and probably ever will. Pretty much everything of what comes next in this video, and in the ones thereafter, is based on a book by Julian C. Sprott called Strange Attractors: Creating Patterns in Chaos. I will link to it in the description to this video. We are going to work with equations called quadratic maps. In these, xt plus 1 and yt plus 1 are determined by some constants, and some multiples of x and x squared, y and y squared, and the product of x and y. Anyway, this is enough of an introduction. Let's get started. So the first thing that we'll do is we'll import the random module, because we'll be working with random values a lot. And the first random values that we'll need are the x and y coordinates of our initial point. So this will be a, well, we'll just say a random starting point, okay? And we'll have a random x, so I'm going to say random.uniform between minus 0.5 and plus 0.5. And then we'll do the same thing with y, so random.uniform once more, minus 0.5 and 0.5. And then we'll print this and see what this looks like. Come on. xy. Run this, and there we go. We have our first random value, our first random point. Run this once more, and it's a different point. So this is working, nice. So now we can use this same setup here to simulate or just draw a random parameter vector, which we'll need for our quadratic map. So here we'll just say that A is also equal to random.uniform. Now I'm going to go with -2 and +2, but if I print this, it's just a single value. So what we'll do is we'll use a list comprehension and say, do this random uniform thing not once but 12 times. So for I in range 12, and then put all of this into a list. I run this again, and there we go. We now have not one, but 1, 2, 3, 4, and so on, all the way up until 12 different values. Now, given this point xy and a random parameter vector, we can now compute the next point. So we can now use this quadratic map. Well, we have to code it first. So compute next point using the quadratic map. Using the quadratic map. How does that work? Well, we have a new x and a new y. The new x is equal to the constant a0 plus a1 times x plus a2 times x squared. So I can just use, or just write x times x here, plus a3 times y, plus a4 times y squared, and lastly a5 times x times y. And now we can copy paste this down here for the y coordinate, but now we have to adjust these numbers here. So we just keep on numbering what we had before, a0, 1, 2, and so on, 5, 6, 7, 8, 9, 10, and 11. So notice that the order of these values here doesn't really change because it's just random values anyway. So you could have 11 up here and 3 here and 1 here, and it really doesn't matter, right? So yeah, it's all random, but we now have x new and y new. So let's see if that worked. Print x new and y new. Run this, and there we go. I'm going to print, just to make sure everything worked, print x and y up here, and there we go. The point has just changed. So let's see if we can make use of this iteratively. So we'll now say for I in range 10, oh come on, geez, there we go. So we have 10 iterations, we'll do this 10 times, but of course we must update x once we have x new, otherwise we'd just be looking at the same value all the time. So update xy. I think that's all we need here. So I'm just going to say x is equal to x new and y is equal to y new, and then we can print x new and y new. We run this, and there we go. Let's bring this up here. We can now see that we have all of these values. Notice how we start out with rather small values of 1.4, so negative 1.4 and positive 1.4 roughly, and now these values, after 1, 2, 3, 4, 5 steps, we are already in the tens of thousands, and then this grows so super quickly. I mean, look at this. This means that we have a 10 with not one, but 154 zeros after it, and then this multiplied with some value up here. So this is an insanely large number. This system here clearly tends to infinity, and if we were to plot this, I mean, you know what, let's do this actually, and let's see what that would look like. So what I'm going to do is I'm going to set up a list in which we'll store all of the points, all of the x and the y coordinates. I'm going to make this 2 lists, and then we'll just append to that list every time that we run through this iterative process, and then we can just visualize these 2 lists. So here, I'm just going to call these, lists to store the entire path or trajectory. Doesn't really matter. So I'm just going to call this an x list and a y list. And at first, the x list is just going to consist of x, this initial point, and then the same thing for y. And now every time that we've updated x and y, we'll store x, y in our list, in our path lists. This is what I'm going to call them. And then we'll say xlist.append.x and ylist.append.y. And now, after we've run this, I'm going to use the pyplot functions. So from matplotlib import pyplot. And now down here, we should now be able to, well, let's first print out the xlist, see if that works. So we've now run 10 iterations, and you can now see that we have all of these values. Now I'm going to say pyplot.scatter. So we'll have a scatter plot. And now we'll plot the xlist and the ylist. And then we must not forget about pyplot.show, because otherwise it's not going to be drawn to the screen. I'm going to run this, and there we go. Here's our cool, strange attractor. Except it's not cool at all. It's in fact pretty boring to look at this because, well, it tends to infinity, and this means that the last point in proportion or in relation to all other points is so much greater that when looking at this, all other points are just crammed together at the origin. This is 0, 0 down here, and we're just shooting off. I mean, the y-coordinate increases like crazy, and the x-coordinate decreases like crazy. And this is just not really interesting to look at. And the problem is that we are shooting off to infinity here and can then only really see 2 points, and we don't want that. So let's rule out this case of us shooting off to infinity. And, well, a pretty simple fix here is just to say, let's check if we converge to infinity. And the way that we can do that is we'll say, well, if x nu is greater than some large value, then this might be a good indication of us shooting off to infinity. Now, this need not be the case. There might be some strange attractor which just involves super large values, and we might be missing that one, but that's not the point. The point is to rule out all of these infinity cases and then focus on those where we are not dealing with these super large numbers. So we'll just say if x nu is greater than a 10 with 10 zeros instead of 1 0, then this is probably too large and we are shooting off. So if x nu is greater than that, or if y nu is greater than this super large number, or, and this is now also important, if x nu is less than minus that. So if we are shooting off into negative territory, so if we are converging towards negative infinity, that's really the same problem. And we'll want to rule that out as well. So, or y nu is less than this. So in all of these cases, we'll say, stop whatever you're doing. And I forgot about the if statement. So we are in this iterative process. So I'm going to say this here. Iteratively pass x, y into the quadratic map. So we will be doing this iteratively, but once we shoot off to infinity, once we converge to infinity, we'll break out of that. And another problem that can happen is that instead of converging to infinity, we might be doing the opposite. We might be converging to a particular point, which then kind of functions like a black hole, which sucks in everything that's happening around it. So at first we might be circling and spiraling around that, but we are getting ever closer towards it. And at some point, we are not really changing there anymore. So x and y, there's just no development there. And we don't want that either, because that's also not cool to look at. So check if we converge to a single point. And how can we do that? Well, if the difference in x and the difference in y, as we are changing between x nu and x, if that's not really happening anymore, if that is too small, if that is below some threshold of minimum movement, so to speak, then we'll break out of that as well. So we can say if x minus x nu, and then we'll just take the absolute value because we are not interested in direction here. If that is less than some arbitrary threshold, and here I'm just going to use this little minus symbol, which then says, well, we have 1 over that 10 with so many zeros, and this means we have some super small value. And if we are below that super small value, then we are not really changing at all anymore. And here, I'm not going to say and instead of or, because this has to apply to both dimensions. So we are perfectly fine in just moving one dimension. But if both dimensions are not really changing anymore, that's when we have probably converged to a single point, and then we'll also break out of this. And yeah, so then we'll break out of this. So if I run this now, and I'm going to add one more thing here, which is print the length of the X list. I'm going to do this. Now, why is it still these 2 points only? Didn't we just rule out these cases? Well, we sort of did. So you can see that the length of the list is only 8. So we did not go all the way up until 10. But the problem is we just broke out of there and we're still visualizing it. So we are just kind of visualizing everything that happened before we broke off the system. Now, how can we fix that? I mean, we only want to look at this when we have found something that's worth looking at. And the way that we can do that is by saying, well, if we have some variable up here, which I'm just going to call found, and I'm going to set that equal to false. And then I'm going to have another variable, which is this convergence thing. So I'm going to call this converging, and I'm going to set that equal to false as well. And now we'll have a while loop, and this while loop will run until we have found something. So while not found, we are running this. And then I'm going to go down here, take all of this and indent this. So this means that while this variable up here, this Boolean called found, is not switched to true, we will always simulate a new starting point, a new parameter vector. We'll then store everything in this list, iteratively pass x, y through that quadratic map, which we are coding down here, and then we'll check if we have converged, if we are converging to infinity or a fixed point and so on, and then we'll just append to that list and so forth. And we'll keep on doing this. And now I'm going to move this converging Boolean inside the while loop actually. So I'm going to put this here. And now, once we've broken out of this iterative loop, I'm not going to make this 1,000 points actually, because 10 points is just not enough to look at a cool pattern. So once we've broken out of this, down here, we'll now check whether we have found something that's worth looking at. So if we are not converging, only then will we set the found Boolean to true. And if that isn't the case, then we'll also be breaking out of this while loop, because then we've found something that's worth looking at, and only then are we visualizing stuff. So let's run this and see what happens. And we get another pattern which looks just like what we had before. So I probably coded a little mistake here. Let's see what the problem is. So the problem is that I've not set the converging Boolean to true. So in here, that is when we check for infinity or the single point, I must say converging is equal to true. Otherwise, it's always going to be false because we just specified it to be false in line 6 here. So converging is set to true in this case and in this case as well. Let's run this once more. And there we go. Now this is the first time that we have produced an image that does not include only 2 points. So we can see that we started, this is probably where we started, and then the system kind of jumped down here, and now it appears to have settled on this trajectory up here, which maybe is now repeating over and over again. So what I'm going to do is I'm going to set this to 10,000 points, and here I'm going to reduce the size of the individual point in our plot from 1 to only 0.1. Let's run this again. And there we go. So again, we started up here, we moved down here, and now the system is just kind of repeating itself. But this is already good progress. So we might choose to only visualize everything after, say, 0.100. So we don't really care about the first couple of points. Let's run this again. And now it's kind of this line here, but that's also, I guess, kind of interesting to look at. So let's run this once more. And here, another pattern where we're just like probably jumping back and forth between these particular clusters. I mean, this might be interesting, but it's not really fascinating, stunning, or whatever. And yeah, the problem is we have only ruled out some of the corner cases of, going to infinity or some fixed point, but we are not checking whether we have found a truly chaotic system. We might have just found something that ends up on a boring loop at some point. Now in the next video to this series, we'll cover chaotic behavior. So we'll introduce something in between here probably that checks for chaotic behavior. And once we've coded that, behavior. Once we have coded that, that's when we will be able to visualize not something like this, but something that's really cool, that's something that's really worth looking at. And oh my God, look at this. This was just by pure luck. I just ran this. I mean, this can happen, but I think this is something that we'll be working towards in the next video. But in the next video, we will make some adjustments to our code, which will produce these images all the time, but not by chance. So let's run this again. I'm going to close this, run this once more. And now again, you can see it's a boring picture, nothing here to see. Run again, another boring picture. I mean, we don't care about these. We want the computer to only produce the super cool ones. And I think you can tell by my voice how hyped I am that just by pure luck, we just produced one of the cool images. And in the next video, we'll make this happen all the time. See you then.